We are going to start now the next lecture, lecture 2 of chapter 2, class 11th mathematics, relations and functions. In our previous lecture, we have studied the definition of the Cartesian product, and now using that definition, we are going to define a relation. So we are saying two non-empty sets A and B, they are given to us. A and B, these are two non-empty sets, and a relation R from A to B is a subset of AB. A cross B, this is the Cartesian product. This product we are saying this is the Cartesian product. And if we take any subset of this set of Cartesian product, then that is called the relation. We are writing R is equal to this, and this is a subset of A cross B, where A cross B is the Cartesian product of the sets A and B. And if an element A, B, it is from this R, then we write it like A is related to B by the relation R. Next definition we have, it is the domain, range and codomain of a relation. So we are saying if a relation R is given from a set A to B, that is R is a subset of A cross B, then the domain of R, it is a collection of all those A. That is, we are saying A comma B, it belongs to R. Then the collection of all these A, that is called the domain of R. So it is all the first coordinates of elements of R is called the domain of R, and all the second coordinates of the elements of R, it is called the range of R. So range of R is basically, we are saying the collection of all these B we are having, that is the range of R. And this set B, this is called the codomain of R. Now if we have number of elements in A that is equal to P and number of elements in B that is equal to Q, then we know that the number of elements in A cross B, that will be equal to P into Q. And we know that every subset of A cross B is a relation from A to B. And how many subsets can be there of this set A cross B? It is 2 raised to the power P into Q number of subsets we have. So the total number of subsets of A cross B that we have, that is 2 raised to the power P into Q, and that is equal to total number of relations that can be formed from A to B. Next we have is the representation of a relation. So in the roster form, first we are talking about the representation of a relation in the roster form. So we are given two sets A and B. Now any relation from A to B, it is the Cartesian product we are talking about. So in the Cartesian product, we are saying A cross B, if we have to write, then the elements we have with minus 2, we will have 0, 1, 4, 9. It is minus 1, minus 2 comma 0, minus 2 comma 1, minus 2 comma 4, minus 2 comma 9. We are writing the Cartesian product. Next we have with minus 1, we will have the elements 0, then minus 1 comma 1, minus 1 comma 4, minus 1 comma 9. Then with 0 we will have these elements like this, then with 1 we will have the elements like this, then with 2 we will have the elements like this. So this is the complete set A cross B. Now we are defining a relation over here. We have taken a subset of this set which contains the elements. We are saying we have taken the elements minus 2 comma 4, minus 1 comma 1, then there is an element over here 0 comma 0, then there will be element over here 1 comma 1, and next we will have an element over here 2 comma 4. So this is a subset of A cross B. This set, it is a subset of A cross B, that is each element of this set is an element of A cross B. So we are saying R is a relation, and this is the roster form of the relation. Now if we have to find the domain of this relation, then we are saying these first coordinates, that is minus 2, minus 1, 0, 1 and 2. So these elements we have collected over here, it is minus 2, minus 1, 0, 1 and 2. These elements, these form the domain of R. When we are talking about the range of R, the second coordinates we are talking about, the second coordinates we have over here, this is 4, 1, 0, 1, 4. So this 1 and 4, these are repeated. So we are writing it is 0, 1 and 4. And codomain of R, that is the set B we are saying, and the set B we have it has elements 0, 1, 4 and 9. This is equal to set B, and this is the codomain of R. Now the second form of representing the relation, it is the set builder form. So we are saying, suppose the set A is equal to 1, 2, 3, 5, and the set B we have that is equal to 4, 6 and 9. We have formed a relation R that is equal to A comma B. It means the relation has the elements from the Cartesian product. This is subset of Cartesian product. And what kind of elements are these? A belongs to A and B belongs to B. And the relation that is given to us over here is, it is A minus B is odd. So if we look at these terms over here, we are saying we have considered an A. Suppose I am talking about, I have to check whether the number 2 comma 6, this belongs to this relation or not. 2 comma 6, it belongs to A cross B. We want to check whether it is a part of this relation or not. So what we are saying? We are saying A belongs to A, B belongs to B. A minus B, if we calculate, it is 2 minus 6. The answer we are getting, it is minus 4, and it is not a odd number. It is not a odd number. So we are saying this is not the part of this relation. So the numbers that will be part of this relation, they will be, we are saying we have to consider A is equal to 1, 2, 3, 4, 5. So first we fix A is equal to 1, and we will see that which values of B should be there. So we are saying the value of B can be 4, the value of B can be 6. For A is equal to 1, B can be 4 or 6. So we have 1 comma 4 and 1 comma 6. These are the elements of the relation. Next, for A is equal to 2, we are writing, this is the set builder form. From set builder form we are writing the roster form. So what we are doing is, we are writing A is equal to 2. For A is equal to 2, B will be equal to 9, because for, if we take B is equal to say 4, then A minus B will be 2 minus 4, that is equal to minus 2. It is even. If we will take B is equal to 6, then A minus B will be 2 minus 6 is equal to minus 4. It is even. So these are not the part of this relation. We are saying these numbers 2 comma 4, 2 comma 6, these are part of the Cartesian product of A, B. But from the Cartesian product we have to choose a subset, and that subset is this subset. We are saying these are the numbers. That is, if we are writing, suppose we are talking about this number 3 and 6, we are saying 3 minus 6 is equal to minus 3, and this is odd. So all these numbers are, all these ordered pairs we have written over here, these form the relation R. Next, the set of first coordinates of these elements, it is 1, 2, 3, 5. A repetition is not allowed in the set. So we are saying the domain of this set, it is 1, 2, 3 and 5, and the range we have, it is 4, 6, 9. Again 4 and 6, these are repeated. So the range of this is 4, 6 and 9, and that is equal to the codomain. In this case, that is equal to the codomain. Codomain is this B. So in this particular case, the codomain and range, they are equal. Next we have is, let R is equal to, this relation is given to us. We are saying R has element x and x cube. X is a prime number less than 10. We have to write the domain and range of this relation. So first of all, we are writing all the numbers over here. So we are saying the relation that is given to us over here, that will have elements, x is a prime number less than 10. So what are the prime numbers less than 10? It is 2, 3, 5 and 7. These are the values of x. So the elements in the relation, it is with the 2, the relation is x and x cube, it is 2 cube. Next element is 3 and 3 cube. Next element is 5 and 5 cube. Next element is 7 and 7 cube. So this is the set we are talking about. This is the relation R in the roster form. Now the first elements we have over here, it is 2, 3, 5 and 7. So these elements, they form the part of the domain of R. When we are talking about the range of R means 2 raised to power 3, 3 raised to power 3, 5 raised to power 3 and 7 raised to power 3. So these values are 8, 27, 125 and 343. So this set, this makes the range of R. In this case, we cannot tell the codomain because it is not clear to us that what are the underlying sets over here. Next, we are talking about R is equal to xy, and x and y are integers, and x into y is equal to 4. We have to find the domain and range. So again, we are writing it in the roster form. So we are saying x into y is equal to 4, and it is given that x and y, these are integers. So we want the integers for which the product is 4. We know that the product will be 4 for 1 into 4, for 2 into 2. Next, if we have minus 1 into minus 4, or we have it as minus 2 into minus 2. Now, if we take the value of x and y as 4 and 1 and minus 4 and minus 1, because it is Cartesian product over here, and we know that this 1 comma 4 and this 4 comma 1, these are two separate terms in this. So we are saying these are the integers, or these are the numbers for which the product will be 4. So we are writing them as ordered pairs. So we are saying the relation R that we have, that is equal to, that consists of the elements minus 4 comma minus 1, minus 2 comma minus 2, minus 1 comma minus 4, 1 comma 4, 2 comma 2 and 4 comma 1. Now if we have to write the domain, so domain is minus 4, minus 2, minus 1, 1, 2 and 4. These elements, they are form the collection of all these elements in the, this forms the domain of R, and these elements minus 1, minus 2, minus 4, 4, 2 and 1, these form the, this set, this forms the range of R. Next we have is the arrow diagram for the set. So we are saying, suppose A is the set 1, 2, 3, 4, 5 and B is the set 1, 4 and 5. Let R be a relation. The relation is less than from A to B. Is less than means we are saying the elements of R, they are of the form A comma B, such that A belongs to A, B belongs to B and A is less than B. So what this collection will be? We are saying, for we are considering 1, both these elements are less than this. So 1 is related to 4 and 1 is also related to 5 by this relation. Next, when we are talking about this number 2, so we have 2 comma 4 and 2 comma 5. Then we have 3 comma 4 and 3 comma 5. Then when we are talking about this number 4, it is less than only 5. So we have number 4 comma 5, and corresponding to this 5, there is no number over here. So this is the relation R that we have given. Now the domain of this relation, it is these elements. It is 1 over here. The next element, it is 2 over here. The next element we have, it is 3 over here, and the next element we have, it is 5 over here, 4 over here. So these are this is the domain of this relation. When we are talking about the range, so range we have the elements 4, 5, 4, 5, 4, 5 and 5. So range is 4, 5. And when we are talking about the codomain, the codomain of R, that is equal to the set B we are talking about. This is the set B we are saying. So the codomain is 1, 4 and 5. Now when we have to draw the arrow diagram, we are saying this is the set A we have and this is the set B that we have. Now in this set A we have 5 elements. It is 1, 2, 3, 4 and 5. In the set B we have 3 elements, 1, 4 and 5. Now by this relation we have 1 is related to 4. This first element we are talking about. Second we have 1 is related to 5. 1 is related to these two elements. Next we have 2 is related to 4 and 2 is related to 5. So we are saying 2 is related to 4 and 2 is related to 5. Next we have 3 is related to 4 and 3 is related to 5. So we have this 3 is related to 4 and 3 is related to 5. And last we have is that 4 is related to 5. So this is the representation of this relation using the arrow diagrams. Next we have is that phi is a subset of A cross B. So phi is also a relation from A to B. We are saying any subset of A cross B is a relation from A to B, and we know that phi is a subset of every set. So what we get is that phi is a relation from A to B, and this relation it is called the empty or the void relation. Next is let A is equal to, this set is given to be x, y and z, and B is equal to 1, 2. Now the number of elements in A, that is equal to 3, and number of elements in B, that is equal to 2. We have to find how many subsets or how many relations can be formed from A to B. So we are saying the number of elements in A cross B, that is equal to 6. So it will have 2 raised to the power 6, that is equal to 64 subsets or the relations. Next is these sets are given to us, these relations, these are given to us, and we have to write the domain and range of these relations. So first relation that is given to us over here, it is R is the relation, and it is x comma y such that x plus 2y is equal to 8 and x comma y belongs to n. We want those values for which x plus 2y is equal to 8. So if we put the value of x is equal to 1, in this we are talking about x and y, these are natural numbers. So if we take x is equal to 1, we will obtain the value of y, that is equal to 7 by 2, and this is not a natural number. So it means we are saying that 1 is not related to any element over here. Next, if we take x is equal to 2, we will obtain y is equal to 3. It means 2 is related to 3. This is R we are talking about. Next, if we put x is equal to 3, we will get y is equal to 5 by 2. Again, this is 3 and 5 by 2, they are not related. We write it like this, that if the two elements they are related, we are writing that 2 is related to 3. But if the element they are not related, we write it like that 3 is not related to 5 by 2. Next we have, if we put x is equal to 4, we will get y is equal to 2. It means 4 and 2 they are related. Similarly, if we put x is equal to 5, it is not related to any number. And if we put x is equal to 6, we are saying 6 will be related to 1. So this is the set R we are talking about. So the domain of this set, that is equal to 2, 4, 6, and range of this set it is 3, 2 and 1. This is the range of the set, and these elements 2, 4, 6, they form the domain of this set. Next is R is equal to xy such that y is equal to mod of x minus 1, x belongs to z, and mod of z is less than equal to 3. So mod function we will study in our next slide. So this function is basically for the sake of simplicity you can just understand that mod function just means that if we put any number in this function, we put any number over here, if suppose I am keeping it as minus 3, it will return the number as 3. This is not the exact definition. Exact definition we will study in our next slides. So this is just for your information right now. So we are saying it just returns the positive number over here. We are putting some number in this and we will get the answer as some positive number, that is called the mod function, modulus function we are saying. So when we are saying it is mod x is less than equal to 3, so mod x is less than equal to 3 means we are saying we want those numbers whose and x belongs to z, we are talking about the integers. So x can have values 0, plus minus 1, plus minus 2, plus minus 3, plus minus 4 and so on. X can have any of these values. Now the next condition we have is that mod of x is less than equal to 3. So if we put 0, so we are saying mod of x will have value 0, 1, 2, 3, 4 and so on. If we put these values over here, the mod values will be 0, 1, 2, 3, 4, so on, and we are saying it should be less than equal to 3. So we are restricted to these values. It means the corresponding values of x we have it is 0, plus minus 1, plus minus 2, plus minus 3. So these are the values of the x that are possible. So this is mentioned over here that the domain of this set it is minus 3, minus 2, minus 1, 0, 1, 2 and 3. Now we have to calculate the range of this set. Now it is given that y is equal to mod of x minus 1. So you can manually calculate these values over here. If you put x is equal to 0, we are saying the values of x and y we are calculating. So corresponding to x is equal to 0, the value of y will be 1, because it is 0 minus 1 mod, that is equal to mod of minus 1, that is equal to 1. Next, when you will put x is equal to 1, you will get 1 minus 1, that is equal to 0. When you put 2, x is equal to 2, you will get the answer is 1. When you will put x is equal to 3, the answer you will get that is equal to 2. So for 3 you will get the answer is 2. Next values of x we have it is, if we put it is minus 1, so we get minus 1 minus 1, that is equal to minus 2 mod, that is equal to 2. So for minus 1 and 3 the answer we are getting it is 2. Now if we put the value of x is equal to say minus 2, we will get it is mod of minus 2 minus 1, that is equal to mod of minus 3, that is equal to 3. So we are saying for the value minus 2, the value of y it is 3, and if we have x is equal to minus 3, then this will become minus 3 minus 1 mod, that is equal to mod of minus 4, that is equal to 4. This is the value of y that we are getting corresponding to x is equal to minus 3. The value of y we have it is 4. So these are the possible values of y. It is 0, 1, 2, 3 and 4. These are the possible values of y, and this makes the range of R. Next we are given A is equal to 2, 4, 5. This is the set A given to us. It is 2, 4, 5. And B is the set. It has element 1, 2, 3, 4, 6 and 8. The relation R is given to be, it has element x and y such that x belongs to A and y belongs to B, and x divides y. So which of these elements these are related, we are saying we have to find which of these elements which are, it is given x divides y. It means if we are checking with 2, that which elements are related to 2, we have to check 2 divides 1, no, 2 divides 2, yes, 2 divides 3, no, 2 divides 4, yes. So it means if we are looking at 2, so 2 is related to 2, 2 is related to 4, 2 is related to 6 and 2 is related to 8. This 2 is related to these elements because it divides these elements. Next, when we are talking about this number 4, 4 does not divide 1, it does not divide 2, 3, it divides 4 and it divides 8. So we are saying 4 is related to two elements, 4 and 8. Next, when we are talking about this number 5, so 5 does not divide any of these elements, any of these numbers. So we are saying 5 is missing from this list. There is no element that is related to 5. So what we get is that the domain of this set, the first element, it has 2, 2, 2, next 4 and 4. So the domain of this set, this relation R, it has elements 2 and 4, and the range of this has the elements, these elements we are talking about, 2, 4, 6, 8, this 4 and 8, these are repeated. So we are saying it is 2, 4, 6 and 8. This is the range of this relation R. Next we have this set A is given to be, it has elements 2, 3, 4, 5, and B has the element 3, 6, 7, 10, and the relation given to us is that X is relatively prime to Y. So we are saying the numbers which are relatively prime to 2, they are 3 and 7. Numbers which are relatively prime to 3, they are 7 and 10. So these are the number listed over here. It is 2, 3, 2, 7. Next, relatively prime to 3, it is 3, 7, 3, 10. Next, the numbers related to 4, they are 3 and 7. Relatively prime means that HCF of 4 and 3, that is 1. HCF of 4 and 7, that is 1. So these two numbers. So it is 4, 3, 4, 7. And when we are talking about this last number 5, so we are saying 5, 3, 5, 6 and 5, 7, these are relatively prime. So what we get is that the domain of this set, it is, this is 2, 3, 4, 5, and the range of this set, it is these elements 3, 7, 10 and 6. These are the different numbers over here. So we are saying the range of this relation R, that is equal to 3, 6, 7 and 10. Next we have is the set A is given to be having the elements 1, 2, 3 and 5, and the set B has the element 4, 6 and 9, and the relation is given by that X and Y, they are related if X minus Y is odd. So again, when we look at these elements, we are saying 1 is related to 4, 1 is related to 6, because in both these cases 1 minus 4, that is minus 3, 1 minus 6 is equal to minus 5. These are odd. But if we are talking about 1 and 9, we are saying 1 minus 9, that is equal to minus 8. So this gives us that 1 is not related to 9. Similarly, for element related to 2, the element related to 2 is 9 only. Next, for elements related to 3, we have 4 is related to 3 and 4 is not related to 3. We are saying 3 is related to 4 and 3 is related to 6. And last, when we are talking about this number 5, we are saying 5 is related to 4 and 5 is related to 6. So these are the elements over here. So the domain of this set, it is 1, 2, 3, 5. So the domain of this set, that is equal to 1, 2, 3 and 5, and the range of this set, that will have elements 4, 6 and 9. So we are saying this A is the domain and this B is the range of this relation R. Next we have is this set R, this relation R is given to be R is equal to X plus 3Y is equal to 12, and X and Y, these are the natural numbers. So we want to find the natural numbers such that X plus 3Y, that is equal to 12. So if we put X is equal to, we are saying the value of X we will have, that is equal to 12 minus 3y. So if we put say y is equal to 1, we will have the value of x that is equal to 9. If we put y is equal to 2, the value of x that we will have it is equal to 6. If we put y is equal to 3, the value of x that we will have that is equal to 3. Now if we put y is equal to 4, then the value of x that we will have that will be equal to 0, and after this all these values will be negative. So we are saying that these are the values for which both x and y, these are natural numbers. So the relation, this relation has the element x, the value of x and y we have it is 9, 1. The value of x and y we have it is 6, 2, and value of x and y we have it is 3, 3. So this relation has 3 elements. So the domain of this relation will be 9, 6, 3. So write 3, 6, 9. The ordering of these numbers in the set, it is immaterial, but ordering of the numbers in this ordered pair, it is important. So we are saying the range is 1, 2 and 3. So the range of R we have it is 3, 2 or 1, or you can write it is 1, 2 and 3. Next is define a relation R from Z to Z. So it is given that R is a relation defined from Z to Z. Given by, the relation is defined by AB, and A minus B is an integer. We have to write the domain and range of this relation. So we are saying if we take any two integers, we are saying you have to write the relation between these two. So we have to take an integer. Suppose we are writing we have taken any integer A from Z and any integer B from Z. Integer B from Z means we are talking about any element of Z, or we are saying it is B is an integer. We know that the difference of two integers is always a integer, and this is what is given to us, that A minus B should be an integer. So we are saying that this thing is true for all values of A when A is an integer, and for all integer values of B. It means the elements that we will have over here, this A, set A, that will be equal to the set of integers, and the set B that is equal to set of integers. So the domain of this relation, it is equal to integers, and range of this relation, it is equal to integers. That is, all the elements, they are related to each other by this relation. Next we have is A is the set, it is 3, 5, and B is the set 7, 9, and this is a relation given that A minus B is odd. So we have to write this relation. So we are saying if we take the first element 3 over here and we subtract it from both these, 3 is not related to 7, 3 is not related to 9, because in both the cases 3 minus 7 or 3 minus 9, the answer is even. Similarly, 5 minus 7 and 5 minus 9, the answer is even. So there is no element in this relation. So we are saying R is the empty relation from A to B. Next is this set A is given. It has element 1, 2, 3, and this set, this relation R is given. Now next we have is the binary relation on a set. So we are saying let A be a non-empty set, then every subset of A cross A, it is called the binary relation, or simply a relation on A. When we are writing relation on A, it means we are talking about A is any set. We are considering the Cartesian products A cross A, and any subset R of A cross A, that is called the relation on A. So since phi, this is written over here that phi is a subset of A cross A, so phi is a relation on A, and this is called the empty or the void relation. Next we have is A cross A is a subset of A, so A cross A is a relation on A, and this is called the universal relation. That is, all elements of A cross A are covered. that is called the universal relation. And the next term we have over here, it is IA is equal to all those elements in which A is related to A, and this relation it is called the identity relation. So suppose these things will be clear to you with the next examples. So for the first case, we have given the example over here. Let A is equal to 1, 2, 3, 4, 5 and R be a relation in A. Then that relation we are talking about R, it is A minus B is equal to 6. Now we can see that we cannot choose any two numbers from this for which A minus B is equal to 6. So there is no element present in this relation, and this is the empty relation, and this relation it is called the void relation or the empty relation. Next we are talking about the set A is given 1, 2, 3. We are talking about A cross A. A cross A has these elements. We have written 1, 1, 1, 2, 1, 3. Then with 2, 1, 2, 2, 2, 3. Then 3, 1, 3, 2, 3, 3. This relation is called the universal relation, because over here we are saying this is just A cross A we are talking about, and that is called the universal relation. Next we are talking about a set A is given. It is 1, 2, 3. And we have written a relation over here that it is 1 is related to 1, 2 is related to 2, and 3 is related to 3. Then this relation is called the identity relation, where we are saying the elements they are A comma A, such that A belongs to A. So this relation it is called the identity relation on A. So these are some particular names. So basically we are talking about the subsets of A cross A. We are saying the empty subset, it has the name empty relation or the void relation. When we are talking about this complete set A cross A, then it has the name universal relation. Out of this we have a subset. We are taking the collection in which we have elements of the form A comma A, such that A belongs to A. Then this relation, this collection it is called the identity relation. Next definition we have, it is the inverse relation. So we are saying let R be a binary relation on a set A. A set A is given and R is a binary relation. Binary relation means R is a subset of A cross A. Then the inverse of R, denoted by R inverse, it is R inverse, is a binary relation on A defined by R inverse is equal to B comma A, such that A comma B belongs to R. So we are saying if we have a set A, say it is equal to 1, 2, we have defined a binary relation on A, that is we have defined a relation that is a subset of A cross A, and let that relation we have, it is 1 comma 2 is the element over here. Then the inverse relation means we are writing the element in the form 2 comma 1. So we are saying in this case we have A is related to B. In R inverse we will have B is related to A. So we invert the position of all the elements of R to obtain the inverse relation. So what we have over here is that this is A is related to B, so A comes, this 1 is over here, then this 1 comes over here. So basically what we have done, that the domain of this relation, this A is the domain of this relation, this becomes the range of the second relation, this B is the range of this relation, and it becomes the domain of the inverse relation. This thing is mentioned over here, the domain of R, that is equal to range of R inverse, and range of R, that is equal to domain of R inverse. So the next question we have is, let A be the set of first 10 natural numbers, R be a binary relation on A defined as follows. This is the binary relation given on A. that two elements A and B, they are related if A plus 2B is equal to 10. We have to express R and R inverse as a set of ordered pairs. So we are saying the elements we will have over here, we are talking about the elements, the value of A that can have it is 1, 2, 3, so on up to 10. The value of A we obtain from this, A is equal to 10 minus 2, B. The values of, these are the values of A and B, all values can have. Now if we put B is equal to 1, we are saying 1. When we put B is equal to 1, the value of A that we will obtain, that is equal to 8. When we put B is equal to 2, the value of A we will obtain, that is equal to 6. When we put B is equal to 3, the value of A we will obtain, that is equal to 4. When we put B is equal to 4, the value of A we will have, that is equal to 2. When we will put B is equal to 5, the value of A we will have, that is equal to 0. This is not possible because A cannot have the value 0. So we are saying the relation R has the elements 8 is related to 1, 6 is related to 2, 4 is related to 3, and 2 is related to 4. This is the relation R. When we have to write R inverse, the inverse relation, we are just writing 1 comma 8. So we are saying in place of 8 comma 1, we are writing it is 1 comma 8. Next, in place of 6 comma 2, we will write it is 2 comma 6. Then in place of 4 comma 3, we will write it is 3 comma 4. And then in place of 2 comma 4, we will write it is 4 comma 2. So this is the inverse relation corresponding to the relation R. Next, we have to show that the domain of R, that is equal to range of R inverse, and range of R, that is equal to domain of R inverse. So if we write the domain of R, the answer we have it is, the domain of R means we are writing these terms over here, it is 8, 6, 4, 2. So it is 2, 4, 6, 8 is the set, and this is equal to the range of R inverse. These elements we are talking about 8, 6, 4, 2. This is equal to range of R inverse. Similarly, when we are writing the range of R, it has the element 1, 2, 3, 4. This set we are talking over here, it is 1, 2, 3, 4, and that is equal to the domain of R inverse.